All right, 6.4, logarithm functions. So we're finally getting to logarithms. So what are they asking us to do here, or telling us we're going to do? And probably the key word here is change. Now, sometimes you do this because you're told to do it, and then sometimes you do it to move the problem forward. It just takes a little bit of practice, but always consider. It's almost like a chess game. I don't know, one of the things in chess, they say always consider checking your opponent when you can. You shouldn't always do it, but consider it. All right, same idea. Always consider converting or changing an exponential equation like y equals a to the x into a logarithmic equation. The logarithmic equation that's equivalent to this would be x equals log base a of y. Always consider making that change if it helps, if it moves the problem or the process or whatever you're doing forward. Now, to be honest, at least in the early parts of this, the author does this too often, but I think he's just trying to show you the toy, show you this little trick. All right, more than that, numerically evaluating logarithms. That's what evaluate means, doing it numerically. Domain and range is not a surprise. Graphing logarithms, solving logarithmic equations, and I had to add this, solving exponential equations that we started in the previous section. We're finally ready to solve an exponential equation. So what I have here is what I talked about a moment ago. Again, this looks so formal to me. I don't know if students are going to appreciate just what it's saying, but it's saying that you can, it's essentially telling you what logarithm is. I write it this way. So I like to say it this way. When you have a logarithm, you have a base and an argument. And this is something that you sometimes calculate. And I guess the best example is if I took the square root of 49 and the square root of 50, I look at these differently. Because 49 is a perfect square, because everything works out. This has a numerical answer to it, 7. This does not have a numerical answer to it. So I still have the square root, and I need to have the square root in the answer. Now what I can do is, simplify this. And 5 square root of 2 is the simplified version. In other words, I could manipulate it, but the square root's never going to go away. And then square root of 51, really nothing I can do with that. It's just going to be square root of 51. So these numbers are just, I should say what we do with square root depends on the number. And that's going to be true for the logarithm as well. So sometimes you just leave what you have. If I had log base 2 of 7, I'd leave it. There's no other way to talk about that point. Kind of be like saying the square root of 51. All right. But what does it mean? What do both these mean? All right. Well, what it means is we are looking for the exponent that I put on the base to get the argument. The exponent we put on the base to get the argument. So it's the exponent I put on 2 to get 7, for example. Now, that one doesn't work very well, so we just leave it this way. But if I'd said log, right next to it, log base 2 of 8. So what is this asking? The exponent I put on 2 to get 8. I'll write it this way. The exponent I put on 2 to get 8. I'm not trying to do a lot of algebra here. I'm just trying to say you should know the answer to this. It's 3. 3 is the exponent. I'd put on 2 to get 8. It's a numerical calculation. In the same way square root of 49 is a numerical calculation. So basically what I'm saying is, if you have the square root of 49, and somebody said, I don't understand, how did you get it? Well, I really can't tell you. You need to know the multiplication table. I mean, there's a lot of math behind this, but it's math that you learned around 4th grade. And the explanation, any explanation I could provide, would seem kind of clunky if you didn't know the number fact. And that's what exactly is going to happen here. The book will try to explain why log base 2 of 8 is 3, but explanations are clunky for something that, you know, you probably learned sometime after you learned square root of 49 was 7 for the first time. In other words, nobody should be surprised that 2 to the 3rd power is 8. That's what they were looking for. What was the exponent? All right, so keep in mind, this is important, but don't let that keep you from understanding logarithms numerically. This was just my attempt to illustrate what I was just saying before. Don't know how clear those were. This is an exponent. Logarithm always is an exponent. 7's the base. X is the argument. When I scramble that, 7 is still the base. Y is the exponent, obviously. I say it's obvious because it's upstairs, superscripted. In other words, we're used to exponents looking like this. And after you scramble, what was the argument is now all by itself. Can't really call it an argument anymore, but I'm going to leave that ARG there. So to give us this example, again, I'm not really pleased with how they're just writing this entire, well, they're writing the entire equation because they're just trying to show you that you can write a number fact 2 different ways. But in practice, you won't be given all of these numbers. In other words, in practice, you might be given log base 2 of 49, log base 7 of 49, and they're asking you, hey, what's the answer? What exponent do we put on 7 to get 49? Well, I think most of us know the answer is 2, because the exponent I put on 7 to get 49 is 2. 7 squared is 49. All right. Well, the other kind of said, well, if you know this fact, 7 squared is 49, you could write this fact. And he's not wrong about that, but like I said, any explanation, I forget what word I used, any explanation for a number fact is pretty clunky. I think that's the word I used. All right, so let's get to, let's just get through what they're trying to do here. So what they're trying to do from here on out on this page is just rewriting. Because you're told to. Change each exponent statement to an equivalent statement involving logarithms, meaning you're given the exponent equation. B is the base. 5 is the, I guess, answer, right? Log base B, and 27 is the argument. So you can take this, scramble it, and get that. That's what they're doing on all of these. Anytime you have an exponent, you can change the logarithm, and the other way around. If you have a logarithm, you can change to an exponent. And that's exactly what they did here. They gave you the logarithm, and they said, no, we want you to change it to the exponent. Make sure you're ready to do this. It's one of the important ideas in the game. Let's look at this last one. So 4 is the base, so that's where it goes. other side of the equal sign, w is the exponent, and this 6 is what I have by itself. All right, look, wrote all over this one. All right. Wrote all over this because this is a very, I don't know, disingenuous page. Very strange what the author does here. Again, I guess there's a reason for it. But what I don't like about it is the other's taking away your chance just to answer the question. Just answer the question. What exponent do I put on? Remember what question this is asking. What exponent do I put on the base to get the argument? What exponent do I put on 3 to get 81? The answer is 4. End of story. We're done. What exponent would I put on 5 to get 1 over 125? Now this one might be a little harder for you to see numerically, and that's fine. We'll use the author's technique to run the calculations. But once you see the answer is -3, you're done. Explanations get really clunky when you have to explain a number. All right. Well, that's what they did. All right. They said, all right, let's take this and call it y. Why did they call it y? I don't know. Call it something. Call it the answer. And then go through the process of solving for y. Not solving for y, but, well, we already solved for y. So call it y, and then go through the process of, you know, the change, and see what you discover about y. I guess that would be the way they're saying it. All right, and what we discover is once we take the exponent and unite with its, the base unite with its exponent and get the 81 out of there, that seems to be the moment we notice that 81 is 3 to the 4th. Again, I hope you see how, you know, disingenuous this is, because if you already knew that 81 was 3 to the 4th, you already knew the answer to that question if you understand logarithms. But we'll play the game, cancel, and we discovered that y is equal to 4. So it's true that the thing we called y is equal to 4. How about log base? Some things I said earlier I had there, but it's not the same now. How about this? All right. So if you don't see the answer right away, by answering the question that logarithm asks, you know, they say it well here. 5 raised to what power equals 125? 1 over 125. That's the question. That's not really what they did here. What they did was not answer the question directly and decided to come up with a game. And the game is call it y, scramble it, and then use something we learned earlier to solve for y. What we learned earlier was if you get the same base here, 5 and 5, you can cancel that and just set the exponents equal, and you find out y equals -3. This is an awful lot of work to answer something that you had to answer anyhow to get the answer. But whatever it takes. If you got that, that's fine. No surprise, you're going to ask domain and range. Domain, remember, is a set of x values. So this is saying x is greater than 0. I'm talking about the domain of the logarithm function, which is also the range of the exponential function is what they're saying. But all right. The range is, well, y can be anything. So the range is y is can be any real number. or just all real numbers. All right, so we know that about the logarithm function. That's going to help us graph it, by the way. We know that x has to be greater than 0. So here's the number line. Here's where x is negative. Here's where x is positive. There's not going to be any graph in these quadrants because x can't be negative for the logarithm function. So the logarithm function is going to graph it's going to be completely contained in quadrants 1 and quadrant 4. I'm just saying that's what we know because x is greater than 0 and y can be both positive and negative. That's going to be important to us later, but right now they just want us to know the domain and range. So when you have a problem like this, I just want you to find the domain and range. I don't want you to, you don't have to do any more than that. Just find it. And the way we find it, that's all they're asking, is take the argument and say greater than 0. Whatever the argument of the logarithm is, doesn't matter what the base is, doesn't matter what I call it, the function here, just the argument. So just immediately pull the argument out. It's x plus 2. That's the thing I'm taking the logarithm of. So it means that's the argument. So x plus 2 is greater than 0. I get x is greater than negative 2, which is correct. All right. How about this one? Here's the argument. Okay. There it is. What do? We just say, you know what? Argument greater than 0. And then solve that inequality. When you solve the inequality, you'll find that, it's greater than 0 between negative 5 and 5. So that would be the domain. So what that's saying is if I put a number that was not in this interval, I'd get an error in my calculator. What if you say, well, 5, 5's not good because that's right on the borderline, but and it doesn't have a square bracket, so I'm not including 5. So 4 would not give me an error in a calculator. If I put in 4, I'd be taking log of what? 9 divided by positive 1. That's a positive number. All I'm worried about is taking the logarithm of a negative number, or 0. So why was 6 excluded? Well, hopefully you see it. 5 plus 6 is 11, but 5 minus 6 is negative 1. And you don't want to do this. You don't want to take the log of a negative number. Log of a negative number is an error on a calculator. So that would not be in the domain. Some properties of logarithm. So they already told us that, the domain, the range, the x-intercept, and there is no y-intercept. X-intercept is 1. We'll go over that. A lot of this will make a lot more sense. There is an asymptote when we start graphing, but that's exactly what's coming up. We want a graph. The graph will be continuous. They tell us some points with the letter A in it. And it will have an asymptote, like they said here, vertical asymptote. So these graphs are kind of familiar. You might recognize this graph from the exponential function. This is y equals a to the x when a is greater than 1. And then what happens, because these are inverse functions of each other, if this point I called a, this point would be the inverse of a. It would just be that graph, that point flipped around. So asymptotes, not asymptotes, inverse functions. This function is an inverse of the logarithm function. Because they're inverses, all of the things we talked about inverses are true, including the graph itself. Now, while this is interesting, you have a choice as to how to, when you actually graph something specific. Well, I guess this is kind of specific. Graphing lnx. So lnx is natural log base e, and so there's the image right there. Make it look a little longer with the asymptote. And it goes on. It's a very slow growing function, but it goes on, growing very slowly outside the box. But let's look at a few more ideas of graphing. And I'll do a part 2 after this one. All right. So actually, I'm going to go ahead and stop right here because this is getting kind of long. We're doing section 6.4, and we'll pick it up in another video.